by Adrian Frankelanson.
Thank you very much. Yeah, so there are cases where you may want to verify your system using this technique called runtime verification. And what do you get? Essentially, you have the following setup. Whereby you have a specification that talks about the correctness of your system, right? And then what you do is you try to check for the correctness of a system at runtime. What do? You run the system in conjunction with another program that's called a monitor, right? And what does this monitor do? It observes the current execution of the system, so what the system is exhibiting currently, right? And it analyzes the events it generates one by one, right? And then eventually it reaches verdicts, right? So you can say that the system satisfies the property or the system violates the property, right? And yeah, and so what is monitorability? Monitorability is precisely, right, the relationship between, on the one hand, you have the operational semantics, right, the verdicts that the monitor gives you, right? And on the other hand, you have the declarative semantics, if you want, of the specification. Why should you care about monitorability? Well, there are a number of reasons. I think one of the main one is that it turns out that for reasonably expressive logics, right, there are a number of properties that you cannot monitor for, right? So in these settings, it is very interesting to understand which properties are monitorables and which ones are not, right? And also, it's also interesting to check whether you can actually describe finitely or characterize these monitorable properties. If you want to build a tool, right, monitorability should also be of concern to you, right? So for example, knowing which properties are monitorable, right, then this gives you hope, right, that you can actually construct a monitor for them, right? Monitorability also gives you an idea of what guarantees to expect from your monitor, or for example, whether the monitor you are synthesizing is correct or not. There are other reasons why you may want to consider monitorability. Okay, so let me give you an overview of what currently exists within this framework, and then I'll tell you what we did in the paper. Okay, so I will start by trying to pin down or give you a general idea of what happens down here, right? So systems, monitors, and instrumented executions. So in RV, you have very little control over the system, right? So here in this framework, we're going to describe the system as a general LTS, right? It's very abstract, right? Monitors, we have slightly more control. So in our framework, we do have a language to describe the monitors, right? And we give it a semantics, right? And the semantics is also another LTS, right? I'm not going to go into how you obtain this, but what you should keep in mind are two things. One is that the system in general, it may be non-deterministic. It may exhibit a different behavior every time you execute it. For example, up here, right? Up here, right? From state P, if you take action A, you kind of go here or there, right? It can be non-deterministic. The other aspect is this one, is that monitor verdicts are irrevocable. So if you're a monitor and you've reached a verdict, right, you are not allowed to change your mind. So you cannot see more events and then say, oops, I'm going to change my mind. Okay, so if you have the system, you have a monitor, right, how do you have runtime executions or monitored executions? Essentially, it is through a process called instrumentation, right? The key idea is that the monitor is not allowed to see the internal state of a system, right? What the monitor does, essentially, it just lets the system execute and it follows it, okay? So, the two key aspects to keep in mind is that one, system behavior is observed in incremental fashion. And the other key aspect is the following, is that the monitor is passive. So in some sense, you are at the mercy of what the system decides to exhibit at runtime. Okay, so for example, up here, right, the monitor reaches a verdict, which is this rejection, which is different from the verdict that it reaches down here. And the reason is that up here, the system exhibits a different behavior than the one down here. Okay? So within the setup, you can define two important predicates, which essentially mean they talk about when the monitor accepts a system, essentially if the system leads the monitor to an acceptance verdict, right? And when a monitor reject system, which is when the system can lead the monitor to the rejection verdict. Okay, so we have described the semantics more or less of what happens here. What about the specifications? So we decided to go for this logic. This is called it is called the modal mu calculus, and there's a reason for this. The reason is that this is one of the most expressive logics around, right? And just to give you an idea of how it works, right? So you have the classical minimal and maximal fixed points, and it has two modalities, right? So the existential modality essentially says, that a system must have at least one transition, A, that leads you to a state that then satisfies psi. And the universal modality is, as you would expect, right? All the A transitions, possibly none, right, lead you to a state that satisfies psi. Okay, so we have defined the semantics here. We can now relate the two. And in particular, we start off by trying to describe what we understand by a monitor monitoring for a property. And there are typically two criteria. The first one is soundness or verdict soundness, and there you say that for all systems, right, whenever the monitor accepts a system, right, then it must be the case that the system is in the property. And whenever a monitor rejects a system, then it must be the case that the system is not in the property. So that's soundness. The other criteria is completeness, which essentially says whenever the system, for all systems, right, whenever the system is in the property, then your monitor should accept it, right? And whenever the system is not in the property, then your monitor should reject it. Now, equipped with this, now we can finally define what we understand by monitorability. So, a formula or a property, phi, is monitorable if there exists a monitor that satisfies these two criteria, okay, soundness and completeness. And a set of formula, right, or a logic, right, is monitorable if every formula is monitorable itself. The bad news is that for the modal mu calculus, right, not all formulas are monitorable, right? And the main result that we have is this one. So this is what we call the maximally expressive monitorable sublogic. So what it means is this. It means that every formula that you can specify in here, you know that it is monitorable. And not only that, any property that is monitorable, you can express in terms of this syntactic fragment. And this is one of the first results in the area that talks about maximality, right? And it is actually very useful if you want to build a tool, right? Because it gives you a basic calculus, right, on what to focus on. But I lied to you a bit, right? So this is not the classical setup. If you look at other pieces of work, and actually most of them, right, this is what you get instead. So the specifications, they don't talk about the behavior of the system, right? So if you want, they are not branching time specifications, but they are linear time. What they talk about is the execution trace, right? So typically, if you look around, right, if you look at most tools, they talk about logics, or they use logics such as LTL, right, which has a linear time semantics, right? If you also consider other definitions of monitorability, the one I showed you, it's not the only definition of monitorability. There are others. They all focus on the linear time semantics, right? Of course, because none of them, they consider the branching time semantics. Right? Currently, there exists no unified theory that allows you to reason both within the same framework about the linear time and the branching time. And this is essentially the topic of this paper. So we try to address these concerns. So in particular, what we want to do is this, right? Because we wanted to keep because of the last point that I mentioned here, right? That we wanted a unified, or we try to get a unified framework, right? What we want to do is this. We want to keep the setup as fixed as possible, right? We don't change this, right? But what we want to change is this specification language, right? And see whether we can obtain, again, the same mechanisms and the same maximality results for this setup. Concretely, as logic, we still stick to the modal calculus. But the modal calculus, it turns out that it has also a linear time interpretation, right? So for example, more concretely, it is defined over a domain whereby you have these traces, LTL style, so you have infinite traces, and it's defined over infinite traces, right? And just to give you an idea, so the diamond modality, right, the existential modality would say, right, that a trace satisfies a diamond A phi if at the head you have an A and the continuation satisfies psi. You satisfy the box modality if whenever at the head you have an A, right, then the continuation must satisfy psi. The logic can express or embed immediately popular logic such as LTL, for example. So this is how you would express them in the modal calculus, linear time. In this new interpretation, you get some different identities. So, for example, in the linear time, this formula, it is a tautology, right? It is valid. But in the branching time setting, this is not. So we are in a slightly different setting. So it's not easily. However, we can still define something similar to what we had before. So we can still talk about when a monitor, right, accepts a trace, or when a monitor rejects a trace, right? And it is as you would expect. What this gives us is that it allows us to recover this picture, the one we had before for the branching time case, but for the linear time case. So here we can have this notion of soundness and completeness, right, by once again universally quantifying overall possible traces, right? Whatever you accept here, it should be in the logic and vice versa, right? Nice thing is that the definition of monitorability remains unchanged, right? We don't touch it. And let me talk a bit about synthesis. We can synthesize in an adequate way most of the operators. So for example, the diamond modality you would synthesize in the following way when you generate a monitor. Essentially, you would generate a monitor that says, whenever I see an A, I continue monitoring according to the continuation. If I see anything else, right, anything else that's not an A, right, I immediately reject. The box, it is dual, right? The conjunction and disjunctions, we can provide a synthesis, but it turns out that there are some complications, right? And let me give you an overview. All the details are in the paper. The idea is that we want to give a synthesis that is as compositional as possible, right? So what we did was we give us a synthesis in a language that's not the language we used originally for the original work. So we have additional operators, right? So then the question was, are we now considering a more expressive model of monitors? Because that would not allow us to remain within the same framework. So what we had to do is show that the additional operators, even though they allow a more streamlined synthesis function, right, they still give you the same expressive power as the original model. Okay, so the first result of the paper, or the first main result of the paper, is that we can obtain once again a maximally expressive, complete monitorable logic, right? And this is it. And those of you who are familiar with process calculi, they would recognize that this is essentially the Hennessy-Milner logic. There are some slight issues. So, for example, there's an issue of tightness. So, what is tightness? The idea is that a monitor is tight if whenever the trace gives it enough information to reach a conclusion, the monitor should reach it at that point, the conclusion. Sometimes this property is also called anticipation. Now it turns out that with our synthesis of operation, right, for certain formula, right, sometimes we obtain monitors that are not tight, right? And the problem for this is that essentially in logic, even in this logic here, you can have some redundancy here, right? So how do we go about it? Well, we define a normalization procedure that is guaranteed to terminate, that takes any formula in here and translates it into a normal form, right? And then we show that for this normal form, our synthesis algorithm always gives you a tight monitor. Yeah, details on the paper. So this was fine and dandy, but then we quickly realized that there is a bit of discrepancy between what we're saying here in this work and what is known out there in the literature. So for example, in particular, the until operator, right, or a property like this would be considered to be monitorable according to other theories. But in our setup, it's actually not. So first of all, if you consider the encoding, immediately you obtain something that uses the minimal recursion operator, right? So it's something that it's not in HML. And actually, you can also give an intuitive reason why they are not, why this would not be monitorable in our setting. The idea is something along these lines, right? So if you consider the trace A forever, right? This clearly violates this property here, right? A until B. Now, since the monitor analyzes things incrementally, right? If there exists a monitor that is complete, it should reject this trace, right? But it should reject it after some finite k, right? So some finite a to the k, right? So if we take this prefix, right, and we append it with a continuation that consists entirely of b's, right, then this would satisfy this property, right? But that monitor, right, would reject this trace, which would make it automatically unsound. So it is reasoning of the sort that you would apply there. So what do? We go back to this picture and we say, listen, soundness, that's not negotiable, okay? I mean, if you get verdicts that are meaningless, I think your monitor is worthless. But what we could negotiate was the completeness aspect. And what we do there is we require partial completeness. What do I mean by this? Partial completeness says that instead of requiring that both satisfactions and violations are then, they have something on this side, you just require one of them. So either you require that for all satisfactions you should accept them, or for all rejections you should reject them. The definition, once again, of monitorability, as we have it here, remains the same. So this doesn't change. Once again, we can prove maximality again. Okay. So and this is the syntactic fragment that is maximally expressive. So everything that you can express that's partially monitorable, you can express in that syntactic fragment. It would make formulas like this monitorable, which is nice, right? We have also a nice curious fact that for specific cases, when you have a finite set of actions, the syntactic fragment that we identified in the branching time case, right, which is this one, actually tends also to be maximally expressive with respect to partial completeness. The reason is that you can express certain things, like, for example, the diamond, you can express it in terms of boxes, right? However, I think the point of monitorability is not to define the minimal calculus. Sorry, it's not to define the minimal calculus, but to define the maximal syntactic fragment, because you want to give as much expressivity as possible. The last point. If you look at what we've achieved so far, it's not really comparing like with like. Why? Because if you consider the branching time case, you can have systems that actually terminate. And the domain that we chose here for the linear time, all the traces, they go on forever, right? Because we chose an LTL style semantics. So what we did, we considered yet another domain, which is what we call infinite, both finite and infinite traces. And you could give the semantics to the modal calculus, and we also obtain another syntactic fragment that is maximally expressive. And that's pretty much it. Just to conclude, so what we have now, in conclusion, is that now we have a unified framework whereby within the same mechanism we can talk about both linear and branching time, right? Immediately, because the logic is so expressive, we can immediately embed things like LTL and CTL within it, right? And what's nice is that now we're well positioned to compare our notion of monitorability with existing notions of monitorability. And I'm done. Thank you very much.
Thank you. So we have one question on Slido. Can you comment on the expressiveness of your monitorable logic fragments? Specifically, how do they compare to past time temporal logic?
So, what kind of past time temporal logic?
Right. I guess. Well, that was my question actually. Okay. Also, I mean, it was also my question. Like, you can look at the past time and take the modality to be the previous operator and just do mu calculus on it.
Yeah.
And if anything on the past should be monitorable.
Yeah. So that would be.
How does it compare to your?
So our the language, maybe I don't know, so the language that we consider for monitors, they're just the regular CCS fragment, okay? So with some extensions, right? So that is the kind of the base language that we have. So we can monitor for things, and that gives you some nice properties. For example, the monitors are always finite state. If you expand any monitor description, right? And you calculate its LTS, it always gives you a finite set of states. And that's nice when you want to synthesize monitors, right? Because you want to keep the monitor state space as small as possible, idea, right? I don't know whether I've answered the question exactly.
Any other questions? Yes.
Thanks for the talk. I don't know if you are familiar with hyper properties and properties by
Good question. Good question.
So I wanted to know if your monitors correspond to safety properties of Albert-Schneider or are something more?
So currently we don't consider hyper properties, right? But that will be one of the natural next steps. Right?
Okay. And well, maybe later I would like to ask you more about the composition of monitors. Okay, thank you.
So I had a question about tightness.
Sure.
Or how can you give any guarantee as to when your monitor will signal, even as immediately as it fails, or would it take? So there was. Would it take much longer? Or
no. So what tightness says, or what we can show here, is that for the notion of full completeness, right? As soon as you have a prefix, right, that you know, for example, that any extension will always be outside of the property, or any extension will always be inside the property, right? Then we can synthesize a monitor, right, that guarantees that. Okay. And we do it in this indirect way by taking a formula, right, that describes that property, removing the redundancy in that formula, and then we can give a one-to-one correspondence.
Any other questions? Okay, so let's thank the speaker.